Welcome to our lesson on graphing rational functions. Couple of learning targets for you in this lesson. I would like you to be able to figure out what the domain and range are of rational functions, so finding those limitations on both the domain and the range, and then to be able to graph those by hand without using your graphing calculator. So first of all, what is a rational function? A rational function is just a function that has this form where we have two functions that are divided by each other. A simple way of saying that is a rational function is a function that is a fraction, where both the numerator and denominator are functions. And the one restriction is we can never divide by 0, so the denominator function can never equal 0, so we'll find some limitations there. And the graphs of rational functions are a little bit different from polynomial functions because they may have breaks in continuity. So all of our polynomial functions were continuous curves. You could put your pencil on a paper and graph the whole thing without lifting up your pencil. But that's not necessarily true for rational functions. We've got a couple of different things that might be excluded from the domain, and those are called discontinuities. One of them is called an asymptote. And an asymptote is just a line, and it's a line where the graph approaches this line, but it never gets there, it never touches. The other discontinuity is called a point discontinuity, and in our graphs, that appears as a hole in the graph. So it's just a point where the value is undefined, and then everything up to it and after it is continuous, but just that one hole is discontinuous. So I've given you a couple of different tables or charts here with a description of vertical asymptotes and point discontinuity. So a vertical asymptote, here's an example in the graph. We represent that with a dotted line, and it's a point where, or it's a line where our graph gets close to that but never gets there. The way to find a vertical asymptote is to find where the denominator is 0. So x equals 3, that's the equation of a vertical line, okay, and so that is the vertical asymptote for that problem. Point discontinuity, over here you see this hole in this line, so that's when we have an equation or a function that simplifies. You can see that this x plus 2 factor can cancel, and we're just left with f of x equals x minus 1. Well, y equals x minus 1 is the graph of a line, but that negative 2 is what makes the denominator 0, and so that is the coordinate, the x-coordinate of where the hole is. To figure out the y-coordinate, you plug in negative 2 to your function that is left. So if I plugged in negative 2 for x, I would get out a negative 3. So negative 2, negative 3 is the point where the hole is. So here's an example. Determine the equations of vertical asymptotes and values of any holes for this graph. So the first thing you always want to do is factor both your numerator and denominator. So when I do that, the numerator is a difference of 2 squares. The denominator, I want factors of 5 that add to 6. So 5 and 1, the signs are the same, they're both minus. And we can see that we share a common factor of x minus 1. So that's going to be a point of discontinuity. That's going to be a hole in the graph, is anything that simplifies there. And then x equals 5 would give us a 0 in the denominator, so that's going to be a vertical asymptote. So just like I said, these simplify, and so we end up having a point where it's undefined at x equals 1 and at x equals 5. Well, the hole is at x equals 1, and the asymptote, is at x equals 5. For some rational functions, the values of the range are limited. So remember, the range are the output values, and this is called a horizontal asymptote, and that occurs when the values of the range are excluded. You can see we have a horizontal asymptote right here. And so here's this example, this is the equation of the function. Okay, so we know that we have a vertical asymptote at x equals negative 2. They don't have that drawn in here, but you can see that that exists. And y equals 1 is excluded from the range. That's a horizontal asymptote. And the way you can find those is by using your table function on your graphing calculator, or algebraically is probably the better way to do that. The horizontal asymptote is the simplified ratio of the leading coefficients. In other words, if I were to go ahead and simplify the leading coefficients of the numerator and denominator, x over x, it's a 1x over 1x, that gives me 1, and y equals 1 is the equation of the horizontal asymptote. So here is a function. We want to go ahead and graph this one. So we can tell right away that it's undefined for x equals 2, so that's going to be a vertical asymptote that you can sketch in. So x equals 2 is a vertical asymptote. Horizontal asymptote, okay, again, if we look at the leading coefficients, we have x over x, so our horizontal asymptote would give us y equals 1. So go ahead and sketch in y equals 1, x equals 2, vertical and horizontal. Then after you sketch the asymptotes, you can pick values of x and calculate some y values and plot some points. So here's what that graph will look like. And I don't know if I had any points in here for you. You can go ahead and just pick any values you want for x and for y and then calculate corresponding values, and you should get that curve. Here's another example. First thing we want to do is to go ahead and factor anything we can. The numerator factors as a difference of two squares. You can see that we have a factor that's going to cancel, so there's a whole at x equals -3. Okay, that's the point that cancels. And so our function simplifies as x equals, or x minus 3, y equals x minus 3. That's the equation of a line. And then -3, -6 is where the whole occurs. The way we find the y-coordinate is to go ahead and plug in x equals -3 into what's left for our function. So we have -3 minus 3, which is where the -6 comes from. So that function looks like that, and at x equals -3, -6 is where the whole occurs. That's it for this video. See you next time.